Today we'll go over lateral directional stability data reduction. As always, calculate your weight and CG before you take off. Ideally for this data you want 2 CGs, one more forward and one more aft. In-flight data requirements, the primary data is aileron position, aileron force, rudder position, rudder force, side slip, and bank angle. Aileron force is coming from a handheld stick gauge. Rudder pedal force will be a pilot estimate based on what they feel they're pushing the rudder pedals with. Aileron position, rudder position, and bank angle will come from your tablet, although you can get bank angle from the pilot's gauge as well. Side slip will become from the yarn that's taped on the wing and the degree marking shown with a grease pencil. First, tabulate all the data in a spreadsheet. You'll have 3 different configurations: climb, cruise, and power approach. And you'll need to share data between the forward CG groups and the aft CG groups. But the data is all the same. It's aileron deflection, rudder deflection, side slip angle beta, bank angle, aileron force, and rudder force. Step 2 is to plot bank angle versus side slip and put both CGs on one plot, but only plot one plot for each configuration. So for this example, we're showing the climb configuration. Blue is the forward CG, red is the aft, and then try to fare a smooth curve between the data points. Step 3 is to plot aileron force versus the same side slip angle beta, again for both CGs. Smooth the curve through the data as shown on the plot. Step 4 is to plot rudder force versus the same side slip angle, again for both CGs. Step 5, plot aileron deflection versus side slip angle for both CGs. Step 6, plot rudder deflection versus the same side slip angle beta for both CGs. And repeat steps 2 through 6 for the cruise and power approach configurations. So as you can see here, the top row is all the climb plots, the middle row is all the cruise plots, and the bottom row is all the power approach plots. And you'll need one for bank angle, aileron force, rudder force, aileron deflection, rudder deflection, and all of them are plotted against side slip angle beta. For spiral stability, plot bank angle and or rudder position versus time. The rudder position helps you understand how the bank angle was set up and when the rudder was removed so that you can get the free response. Note whether the bank angle is converging, steady, or diverging as time progresses. For Dutch roll data reduction, plot bank angle and or yaw angle versus time and determine the damping ratio and the period of the Dutch roll. Then calculate the undamped natural frequency. As you can see for this example on the bank angle trace, there's a period of about 3 seconds, and then using the half cycle amplitude is about 1.33, and using that chart on the right, 1.33 goes in on the x-axis, and you'll see that the damping ratio is approximately 0.1. The damped natural frequency is 2 pi over the period, or for this example it's 2.09 radians per second. And to get the undamped natural Dutch roll frequency, use that equation shown with 2.09 in the numerator and the square root of 1 minus 0.1 squared in the denominator, or 2.10 radians per second.